Hello and welcome to DAR Tutors. Today, we'll be covering vectors in space, which is a fundamental topic in IB mathematics, applications and interpretation at the higher level. Our focus will be on understanding 3D vectors, their magnitudes, performing vector algebra, and defining the scalar or dot product. By the end of this video, you will be able to perform these operations proficiently. Let's begin by introducing the three-dimensional Cartesian coordinate system. In this system, we use three mutually perpendicular axes, the x, y, and z axes, to locate any point in space. A point P in space has coordinates x, y, z. Its position vector is the vector that originates from the origin O and terminates at point P. We denote it as OP with an arrow on top, or just the lowercase bold letter p. In component form, this position vector is written as a column vector with elements x, y, and z. Alternatively, we can express the position vector using base unit vectors. The base unit vector I is a vector of length 1 in the positive x direction. The base unit vector j is a vector of length 1 in the positive y direction. And the base unit vector k is a vector of length 1 in the positive z direction. So, the position vector of P can also be written as x times I plus y times j plus z times k. Both component form and unit vector form represent the exact same vector. For our first objective, let's learn how to find the magnitude or length of a vector. The magnitude of a vector is simply its length. We can visualize this using the Pythagorean theorem in 3D. Consider a position vector A with components A1, A2, and A3, which points from the origin O to a point P. The magnitude of vector A, denoted by AE, is the distance from the origin to the point P. We can calculate this by applying the Pythagorean theorem twice. Let's see this in action with an example. We will calculate the distance from the origin to the point A with coordinates 0, 2, 0. Here, the position vector for point A is OA, which is a column vector with components 0, 2, and 0. This means point A lies on the y-axis at a distance of 2 units from the origin. Using our formula, the magnitude of OA is the square root of 0 squared plus 2 squared plus 0 squared. This simplifies to the square root of 4, which is 2. Now let's try a point that is not on an axis. B with coordinates 3, 0, 2. In this case, the position vector is OB, which has components 3, 0, and 2. Using the formula, the magnitude of OB is the square root of 3 squared plus 0 squared plus 2 squared. This gives us the square root of 13. Let's confirm our understanding. You are now able to calculate the magnitude of a 3D vector. This is a vital tool for finding distances in space. Next, we'll cover operations with vectors in space. This is our second objective for this scene. Our goal is to understand how to perform vector addition, subtraction, and scalar multiplication. Because visualizing these operations can be difficult in 3D, we rely on component form. The rules for these operations extend directly from 2 dimensions to 3. It's essentially performing the operation on each corresponding component. To add 2 vectors, you add their corresponding components. This represents placing the vectors head to tail to find the resultant vector. To subtract one vector from another, you subtract their corresponding components. This is equivalent to adding the negative of the second vector. When you multiply a vector by a scalar k, you multiply each component by k. This creates a new vector that is parallel to the original, but with a length scaled by the absolute value of k. Let's work through an example to solidify this. Suppose we have vector A and vector B. Vector A is your 1, 3, 2, and vector B is 3, 0, 1. First, let's find the sum, A plus B. We add the corresponding components. 1 plus 3 is 2, 3 plus 0 is 3, and 2 plus negative 1 is 1. The resulting vector is 2, 3, 1. Now let's try a more complex operation. 2a minus b. First, we calculate 2a by multiplying each component of a by 2. This gives us 6, 4. Next, we subtract b from this new vector. That's 2 minus 3, which is 5, 6 minus 0, which is 6, and 4 minus 1, which is 5. The final vector is 5, 6, 5. Finally, let's find the product of a scalar magnitude and a vector, magnitude of a times b. Remember, the magnitude of a vector is a scalar number, so this is a scalar multiplication. First, we find the magnitude of a, which is the square root of 14. Then we multiply each component of b by this scalar root 14. This gives us 3 root 14, 0, negative root 14. As you can see, the operations on vectors in component form are straightforward and follow logical rules. We've now met our objective by performing vector addition, subtraction, and scalar multiplication. Our third key concept is the vector between 2 points. Our goal here is to learn how to express this vector and understand its significance. The vector between 2 points, A and B, is known as the displacement vector, AB. It represents the direct translation or journey from point A to point B. Using the triangle rule for vector addition, we can get from A to B by first going from A to the origin, and then from the origin to B. This translates to the vector equation. Vector AB equals vector AO plus vector OB. Remember that vector AO is the negative of the position vector OA, so we can write this as OB minus OA. So, the displacement vector from A to B is found by taking the position vector of the terminal point B and subtracting the position vector of the initial point A. Let's write this in component form for 3D points. If point A is A1, A2, A3, and point B is B1, B2, B3, the vector AB is simply B1A1, B2A2, B2A3. This vector describes the step-by-step movement in the x, y, and z directions to get from A to B. Let's apply this to an example. We are given 2 points, P and Q. Point P has coordinates 3, 1, 2, and point Q has coordinates 1, 1, 3. First, let's write down the position vectors. The position vector for P is simply the vector with its coordinates as components, which is 3, 1, 2. Now, to find the vector PQ, we subtract the position vector of P from the position vector of Q. That's 1, 1, 3, minus for 3, 1, 2. Subtracting the components gives us 1, 3, 1, 1, 3, 2, which simplifies to 4, 2, 1. This vector tells us how to get from P to Q. We can also find the distance between the 2 points, which is the magnitude of the displacement vector PQ. Using our magnitude formula, we calculate the square root of 4 squared plus negative 2 squared plus 1 squared. This is the square root of 21 units. So, we've successfully learned how to determine the displacement vector between 2 points by subtracting their position vectors. This allows us to quantify the movement between any 2 points in space. We now come to the concept of parallelism. This is a crucial idea that underpins much of our work with vectors, and it's our next learning objective. Our goal is to understand the condition for 2 vectors to be parallel. The rule is simple and profound. 2 non-zero vectors are parallel if and only if one is a scalar multiple of the other. This means that if we can write vector A as a constant k times vector B, then they are parallel. This constant k scales the vector's length and can flip its direction if k is negative. If A equals k times B, they are parallel. Consequently, the magnitude of A will be the absolute value of k times the magnitude of B. Let's work through an example to find unknown components in parallel vectors. We'll use the technique of equating corresponding components. We are given 2 parallel vectors, A and B, with some unknown components R and S. Since they are parallel, we can write A equals k times B. In component form, this means the vector 2 or 1R equals k times the vector S2, 3. To find our unknowns, we can form an equation for each component. Equating the x, y, and z components gives us a system of 3 equations. 2 equals k times s, negative 1 equals k times 2, and r equals k times negative 3. The second equation is key because it contains only one unknown k. We can solve it directly. Dividing by 2, we find that the scalar k is negative 1/2. This means vector A is half the length of vector B and points in the opposite direction. Now that we have k, we can substitute it back into the other 2 equations to find r and s. Using equation 1, we get 2 equals negative 1/2 times s, which gives us s equals negative 4. And using equation 3, we get r equals negative 1/2 times negative 3, which gives us r equals 3/2. By using the definition of parallel vectors and equating corresponding components, we have successfully found the unknown values. We now understand that parallel vectors are scalar multiples of each other, which is our objective met. A special type of parallel vector is a unit vector. Let's make that our next learning objective. Our goal is to define unit vectors and learn how to normalize any vector to have a length of 1. As the name suggests, a unit vector is any vector that has a magnitude of exactly 1 unit. This means that if we calculate its length, we will always get 1. Unit vectors are used to indicate direction without also carrying information about length. How can we create a unit vector from an existing vector? This process is called normalizing the vector. To find a unit vector in the same direction as a given non-zero vector A, you divide the vector A by its own magnitude. Think of it as shrinking or stretching the vector until its length is exactly 1, while preserving its direction. This special unit vector is denoted by a hat, pronounced a hat, and is used to represent the direction of vector A. Let's work through an example. Suppose we want to find a vector that has a specific length and direction. We need to find a vector B that has a length of 7 units and points in the opposite direction to vector A. First, we need to find the direction of A. We do this by calculating its magnitude, the square root of 2 squared plus -1 squared plus 1 squared, which is the square root of 6. The unit vector in the direction of A hat, is then 1 over root 6 times the vector A. Now we can construct our desired vector B. We want the vector B to have a length of 7, so we multiply by 7. We also want it to be in the opposite direction, so we multiply by -1. Therefore, vector B is -7 times our unit vector a hat. This gives us the vector B, which is 7 root 6 times 2, 1, 1, satisfying both the length and direction conditions. We have now learned that a unit vector has a length of 1, and we can find it by dividing a vector by its magnitude. We have also seen how to use this concept to find vectors with specific lengths and directions. Objective met. We've discussed parallel vectors, but what about points? Let's talk about collinear points. Our objective for this section is to understand the definition of collinear points and how to prove it using vectors. Simply put, 3 or more points are collinear if they all lie on the same straight line. To prove that points A, B, and C are collinear using vectors, we need to show 2 conditions are met. First, the vector AB must be parallel to the vector BC. Second, the point B must be a common point to both segments. If both conditions hold, then A, B, and C must lie on the same line. Let's work through an example to see how this proof works. We want to prove that the 3 points A, B, and C are collinear. To do this, we need to calculate the vectors AB and BC. First, vector AB is found by subtracting A from B, 4, 1, 2, 3, which equals 5 to 2 to 4. Next, vector BC is found by subtracting B from C, 14, 4, 4 to 0, 9, 1, which equals 10 to 4 to 8. Now we need to check if one is a scalar multiple of the other. Let's compare the components of BC and AB. If we divide each component of BC by the corresponding component of AB, we get 10 divided by 5 is 2, 4 divided by 2 is 2, and 8 divided by 4 is 2. The scalar is 2. Since vector BC is 2 times vector AB, we have proven that the vectors are parallel. Because they share a common point, B, the points A, B, and C must lie on the same straight line. We have now defined collinear points and demonstrated how to prove they are collinear by showing that displacement vectors between them are parallel and share a common point. This fulfills our objective. A very useful application of vectors is defining geometric shapes. Let's focus on parallelograms. Our objective is to use vectors to identify and find properties of parallelograms. A key property of a parallelogram is that its opposite sides are parallel and have equal length. This can be expressed perfectly using vectors. The vector from A to B must be identical to the vector from D to C. That is, vector AB equals vector DC. This property gives us a powerful method to find the coordinates of a missing vertex if we are given the other 3. This is an IB-style question you are likely to encounter. Let's work through an example. We are given 3 vertices of a parallelogram ABCD and asked to find the coordinates of the 4th vertex, C. First, we set up the vector equation based on the property we just discussed. We'll let the unknown coordinates of C be A, B, C. The property gives us the equation, vector DC equals vector AB. Now we find the component forms of these 2 vectors. Vector AB is found by subtracting A from B, which gives 3 or 2, or 2. Vector DC is found by subtracting D from C, which gives A3, B1, C4. Next, we set the components equal to each other. Since the vectors are equal, their corresponding components must be equal. This gives us three simple equations. A -3 equals 3, b minus 1 equals -2, and c minus 4 equals -2. Solving these equations gives us a equals 6, b equals -1, and c equals 2. Therefore, the coordinates of vertex C are 6 to 1, 2. At the 10-minute mark of this video, I'd like to include a call to action. I hope you're finding this video helpful. If you need more personalized support in IB A-Level or IGCSE curricula, please contact Dart Tutors for expert online or home tuition. We'd love to help you succeed. This vector method is a very reliable way to solve parallelogram problems. A good practice is to always double-check your answer, for example, by ensuring the midpoints of the diagonals are the same. A parallelogram's diagonals bisect each other, meaning they meet at the same midpoint. We can verify our answer by calculating the midpoint of diagonal DB and diagonal AC. As you can see, both midpoints are identical, confirming our answer is correct. We have now seen how vectors can be used to prove properties of parallelograms and find missing vertices. We now move on to a new type of vector multiplication. Previously, we learned about scalar multiplication, which produces a parallel vector. Now, we'll learn about the scalar product. Our objective is to define the scalar product and understand how to calculate it using component form. When we multiply two vectors, there are two distinct ways to do it. One gives a scalar, a number, and the other gives a vector. The scalar product, also known as the dot product, produces a scalar answer and is written with a dot between the vectors. Be careful not to confuse this with scalar multiplication, which involves a vector and a scalar. The other is the vector product, or cross product, which produces a vector. This will be covered in a later lesson. For the scalar product, the calculation is quite simple. You multiply the corresponding components of the two vectors and then add all the results together. Let's work through a two-dimensional example first. Let's find the dot product of the vector 2, 3 and the vector 1, 4. We multiply the first components, 2 and 1, and add the product of the second components, 3 and 4. This gives us 2 plus 12, which equals 14. Notice the result is a single number, a scalar, not a vector. Now let's do a three-dimensional example. We'll find the dot product of the vector 1, 2, 4 and the vector 3, 1, 2. We multiply the first components, the second and the third, and then sum the products. That's 1 times 3 plus 2 times 1 plus 4 times 2. This gives us 3 plus 2 plus 8, which simplifies to 7, again a scalar result. In this scene, we have successfully defined the scalar product, or dot product, of two vectors and learned the component-wise calculation. This scalar result provides valuable information about the angle between the two vectors, which we will explore next. The dot product is more than just a calculation. It has important geometric properties. Our objective in this scene is to explore these properties. Our goal is to understand the algebraic rules governing the dot product and a crucial geometric identity. First, let's look at the algebraic properties. These are similar to the rules you know for multiplying numbers. The dot product is commutative, meaning the order doesn't matter. A dot B is the same as B dot A. It's also distributive over vector addition, so a dot B plus C can be expanded just like in algebra. While these are useful, a much more important property connects the dot product to the magnitude of a vector. This identity states that the dot product of a vector with itself is equal to the square of its magnitude. This makes sense. A dot A is A12 plus A22 plus A3.2, and the magnitude squared H2 is also A12 plus A2.2 plus A3.2. This identity will be incredibly useful. Now, let's explore the most significant geometric property. The dot product provides a way to find the angle between two vectors. This is a key formula in vector geometry. This formula connects the algebraic calculation of the dot product to the geometric angle. By rearranging the formula, we can make finding the angle the subject. The cosine of the angle is the dot product of A and B, divided by the product of their magnitudes. This relationship is particularly powerful when the angle is 90 degrees. If two vectors are perpendicular, or orthogonal, the angle between them is 90 degrees. The cosine of 90 degrees is 0. This means that if the dot product of two non-zero vectors is 0, they must be perpendicular. This is a fundamental test for perpendicularity. In this scene, we have covered the algebraic properties of the dot product and, Most importantly, it's geometric interpretation for finding the angle between two vectors and for testing perpendicularity. We've achieved our learning objective. Let's put the geometric property of the dot product to use in a practical problem. Our objective is to determine the type of triangle given its vertices. We can do this by examining the angles within the triangle. For a right-angled triangle, we need to show that the dot product of two side vectors is 0. Let's consider this triangle with vertices A, B, and C. To determine if it's right-angled, we need to find the vectors representing two of its sides that share a common vertex. For example, the vectors AB and AC. First, vector AB is found by subtracting A from B, which gives 1, 6, 11. And vector AC is found by subtracting A from C, which gives 3, 2, 4. Now, we will test for perpendicularity by calculating the dot product of these two vectors. The dot product AB dot AC is 1 times 3 plus 6 times 2, 11 times 4. This equals 3, 12 plus 44. The result is 29, which is not 0. This means the angle at vertex A is not 90 degrees. So, the triangle is not right-angled at A. To be thorough, we should check the other two possible right angles, at B and C. Let's check the angle at B using vectors BA and BC. Remember, vector BA is the negative of vector AB, so it's a 1 or 6, 11. Vector BC is found by subtracting B from C, which is 4, 8, 7. Calculating their dot product. Atom are 1 times 4 plus 6 times 8 plus 11 times 7 equals 4 plus 48 plus 77, which is 129, not 0. So, no right angle at B. The last possibility is the angle at C. We'll use vectors CA and CB. Vector CA is the negative of AC, so it's 3, 2, 4. Vector CB is the negative of BC, so it's 4, 8, 7. Their dot product is 3 times 4 plus 2 times 8 plus 4 times 7 equals 12 plus 16 minus 28, which is 0. Since the dot product of CA and CB is 0, the angle between them is 90 degrees. Therefore, triangle ABC is a right-angled triangle with the right angle at vertex C. Once we know it's a right-angled triangle, finding its area is straightforward. The area is 1/2 times the base times the height, where the base and height are the lengths of the two perpendicular sides. That is, half the magnitude of CA times the magnitude of CB. We've now met our objective of using vectors to determine triangle properties. Let's work through one final HL-level example problem that combines several concepts we've learned. Our objective here is to find an unknown scalar by applying the condition for perpendicular vectors, and then to find the area of the resulting triangle. The problem states that vector A is perpendicular to vector B, and we need to find the scalar k and then the area of the triangle formed by these two vectors. First, for part A, if the vectors are perpendicular, their dot product must be 0. So we calculate the dot product of y1, 2, k and whole k3, 2 and set it equal to 0. Multiplying corresponding components and adding gives us 1 times k plus 2 times 3 plus k times 2 all equals 0. This simplifies to k plus 6 plus 2k equals 0. Solving for k, we find that k must be equal to 6. Now we know our two vectors. Vector A is /1, 2, /6, and vector B is /6, 3, 2. These two vectors are perpendicular. For part B, we need the area of the triangle formed by these two vectors. We can find this area using a geometric property of the dot product. The area of a triangle with two sides given by vectors A and B is 1/2 times the magnitude of A times the magnitude of B times the sine of the angle between them. However, we already know the angle is 90 degrees. Since the vectors are perpendicular, the angle is 90 degrees, and the sine of 90 degrees is 1. So the formula simplifies to 1/2 times the magnitude of A times the magnitude of B. Now we just need to find the magnitudes of vectors A and B. The magnitude of A is the square root of 1 plus 4 plus 36, which is the square root of 4. The magnitude of B is the square root of 36 plus 9 plus 4, which is the square root of 15 or 7. Finally, the area of the triangle is 1/2 times root 41 times 7, which equals 3.5 times root 41 square units. In this problem, we've successfully combined the concepts of perpendicularity and magnitude to solve a complex vector geometry problem, achieving our objective. Let's summarize the key concepts we've covered today. You are now equipped to handle a variety of IB-style vector problems. First, we established the coordinate system for vectors in 3D space, using both component and base unit vector forms. Second, you learned to perform vector addition, subtraction, and scalar multiplication by operating on corresponding components. Third, you can now calculate the magnitude or length of a vector using the 3D Pythagorean theorem. Fourth, you understand the condition for parallel vectors, which are scalar multiples of each other. Fifth, you learn to find the displacement vector between 2 points, a fundamental skill for describing motion. Sixth, you can define and calculate unit vectors, which represent direction only. Seventh, you know how to perform the scalar or dot product, which results in a scalar. And finally, you've seen how the geometric property of the dot product allows us to find the angle between vectors, test for perpendicularity, and prove collinearity. These are the essential tools you'll need for vectors in space. Now, let's practice with some IB-style questions. It's time to test your understanding. Here are 5 practice questions. I'll read each one, and you can pause the video to work through them on your own. After a few seconds, the solution will be revealed. Question 1. Given vectors p equals ∀1, 4, 3, and q equals x, 2, y. Find x and y if vector p is parallel to vector q. Pause the video and try to solve it. Solution. Since p is parallel to q, p must be a scalar multiple of q, i.e., p equals kq. This means 1 equals kx, 4 equals 2k, and 3 equals ki. From the second equation, k equals 2. Substituting into the first and third equations gives 1 equals 2 and 3 equals 2y. Solving for the variables, we get x equals 0.5 and y equals 1 point. Question 2. Points A, B, and C are 3, 1, 2, 1, 0 to 1, and 2, 5, t, respectively. Find the value of t for which the triangle ABC is right-angled at B. Pause the video now. Solution. For the triangle to be right-angled at B, the vectors BA and BC must be perpendicular. Their dot product must be 0. First, find BA by subtracting A from B, which gives 4/1/3. Then find BC by subtracting B from C, which gives 1, 5 TP1. The dot product BA dot BC is 4, 1 plus 1, 5, 3, 2, 1, equals 0. This simplifies to 4, 5 turn 3 to 3 equals 0, which means 4, 3 t equals 0. Solving for t, we get t equals 4, 3. Question 3. If vector v equals 2i plus j minus 2k, find a vector w of length 15 units that is parallel to v. You can pause now to solve. Solution. We need to find the unit vector in the direction of v hat, and multiply it by 15. The magnitude of v is the square root of 2 squared plus 1 squared plus negative 2 squared, which is the square root of 9 or 3. The unit vector v hat is 1, 3 times 2, 1, 2. Multiplying this by 15 gives w equals 5 times 2, 1 or 2, or 10. 5, 10. Question 4. Show that the quadrilateral ABCD with vertices A1, 2, 3, B3, 3, 2, 7, 4, 5, and D5, 1, 6 is a parallelogram. Pause and try to prove it. Solution. To prove it's a parallelogram, we can show that one pair of opposite sides are represented by equal vectors. Let's check AB and DC. Vector AB is 2, 5, 1. Vector DC is 5 to 7, 1, 9, 4, 6, 5, equal 2, 5, 1. This is incorrect based on the notes. Let's recalculate based on the provided points. Vector AB is B minus A, which is 3 to 1, 3, 2, 2, 3, equals 2, 5 to 1. Vector DC is C minus D, not D minus C. Wait, the problem says AB and DC. Let's recalculate vector DC. It should be C, CD, so 7, 5 of 4 to 1, 5, 6, equal or 2 at 5 are 1. Vector AB and vector DC are equal. Therefore, the quadrilateral is a parallelogram. Alternatively, we could show that the diagonals AC and BD bisect each other by finding their midpoints. The midpoint of AC is 4, 1, 4, and the midpoint of BD is also 4, 1, 4. Since the midpoints are the same, the diagonals bisect, and it is a parallelogram. Question 5. A sphere has center C 1, 2, 4, and diameter AB, where A is 2, 1, 3. Find the coordinates of B and the radius of the sphere. Pause and find the solution. Solution. The center C is the midpoint of the diameter AB. This means vector CA and vector BC are equal. Vector CA is A minus C, which is P1 A1 S1. Let B be X, Y, Z. Vector BC is C minus B, which is 1X, 2Y, 4I. Setting CA equals BC gives a system of equations that yields X equals 0, Y equals 3, Z equals 5, so B is 0, 3, 5. The radius is the magnitude of the vector CB. CB is Y1, 1, 1. Its magnitude is the square root of 3. That brings us to the end of our lesson on vectors in space. We've covered the foundational concepts and applied them to various geometric problems. You are now equipped with a solid understanding of this topic for your IB/AI/HL exams. If you need more help, remember that you can find more resources and personalized tuition at DAR Tutors. Thank you for watching.